So good morning all of you. We will basically start from the point where we left. We were not yet done with the Nyquist criteria for ISI avoidance, but mostly I think 98-99% of what I wanted to say I had done in the last lecture. Only a few things are remaining which we will cover in this lecture. So let us, I think, start from what we were doing. So there are two motivating concepts, two motivating / need of the hour. You can say need of the hour are reasons for studying ISI. Studying pulse shaping to avoid ISI. So one is our problems with pulses that are, you can say, that somewhat extend too much in time. That somewhat extend too much in time. Okay. Somewhat exist for too much time. Which means there's a sync pulse. The sync pulse consumes a lot of time. Okay, for generating it, you will need at least a lot of time to generate it and then to use it. The issue can be surpassed by having a delay in the system. Okay, but this delay, what happens is that once you put a delay in the system, at the receiver you have to wait for that much time to decode the information. I think this we discussed in one of the initial lectures, maybe when we were discussing why we need to have an anti-aliasing filter. Okay, so you can refer to that lecture, or you can refer to that textbook where we took our content from. Okay, so one of the issues is that we do not want pulses which are consuming a lot of time. But the problem is if they are time limited, then they become band unlimited. Okay, it means they will consume a more bandwidth. Now, if they consume more bandwidth, then again there is an issue. Okay, with them consuming more bandwidth, they will lead to again ISI. It means several pulses will try to, you can say, interfere with each other. I think that I had written here. Last lecture also I went to that point and showed it to you. Okay, so maybe it is in the lecture before. Yes. So you may go back and see lecture 14 where we discussed that if the pulses are time limited, then what is the issue, and if they are band limited, then what is the issue? If they are band limited, then ultimately it leads to pulses being consuming more time, and that leads to ISI. And if they are time limited, then again in the band they have a lot of bandwidth consumption and they cannot be band limited. Okay. Second problem or the second issue is channel being band limited. Okay. Channel being band limited. Okay. So these are the two major factors which say or which dictate or which force us to basically consider pulse shaping as one of the study points. Okay, and that is what Nyquist did, and we studied what he did. Okay, so basically what he said was that we can have overlap in, you can say, frequency domain, but that overlap has to be somewhat manageable nature. Okay, so we said that the design should be like this, that it should be odd about this point, so that once you have another pulse, so in this region, let us say this is the region, if I add both these pulses, that is if I add signal 1, this is signal 1, suppose this is, and this is 2. So if I do 1 plus 2 for all the times in duration, let us say this is t. So for all t in t, you can say, this is not very good way to write, but I'm just writing for all t in t, this should add to a constant. Okay. So BP Lathi gave a somewhat, you can say, an easy proof of this, that how this spectrum should be. How this should be. So this should be, let us say, odd about this point. If it is odd about this point, then this criteria can be easily satisfied. And this criteria being satisfied, the Nyquist first criteria for ISI avoidance is satisfied, and you can have pulses which have a greater roll-off factor. Okay, रोल ऑफ फैक्टर ज़्यादा होगा तो उसमें क्या होगा कि उनका जो इफेक्ट है फॉर ग्रेटर टाइम विल बी रिड्यूस्ड. That is what we were doing. I think this is what the criteria was. So in the frequency domain, your spectrum should be such that if you shift it by r, it should all add up to a constant number. That is the bit interval. You can say TB is the bit interval, not the bit rate. Okay, you should remember the difference between bit interval and bit rate. Bit rate is number of bits per second. Bit interval is the time taken by a single bit, and they will be reciprocal of each other. I think that is very much clear to you. But just to be, you can say, good on time, means you know this, so you should be specific in saying bit interval or bit rate. So we saw that, and it was derived that this should be the case. And they said that if p of x is real and that too positive, then it is easy to understand that the absolute value should satisfy this relationship, but the condition was real valued and positive. Then only this equation is equal to this equation. That is what I wrote, I think, in the last lecture. This you should remember. Once doing this derivation, we showed or we saw that this happens. We are not digging very much into the proofs. I told you that if at all you need a very proper proof, you can read Couch's book. The author has given the proof in somewhat in a more involved manner. But right now, for understanding, for general understanding at this level, this is fine. At least I would say that this is fine. Okay. But if there is someone who is more interested, you are most welcome to go there, read, and if you have any doubts, we can have a separate session and discuss. Okay. So this is what I explained, that how you will have this concept. You put a mirror and then just see inside the mirror and then flip it. Quite easy to understand. Okay, then we studied the concept of excess bandwidth, Vt. It means that the pulse will now take, instead of r by 2, it will take 1 plus r into r by 2. जो सबसे कम bandwidth लेती है, that is the sync pulse. We know that this is the pulse which will consume the least possible bandwidth for a given bit rate r. Okay, तो sync pulse सबसे अच्छी pulse है in terms of consuming the least possible bandwidth. But there are several issues with the sync pulse. Okay, you cannot easily use it in the time domain. So we want pulses which doesn't increase our engineering, you can say, hardships. Engineering hardships means there is a concept in theory, but really if at all you need to put it on the road, if you need to use it, then there are a lot of issues in the hardware. तो ऐसा नहीं होना चाहिए. So that's why we basically have to allow the pulses to exceed the bandwidth of hardware. इसका जो I think motivation था, we studied from Upamanyu Madhu's book, and I think wrote it down in the start. Yeah. A pulse decaying at 1 by TB. I think this is what I have taken from there, and this is a very good explanation I found out for us to understand the concepts. Okay. Then we saw this raised cosine spectrum, which satisfies this condition. Okay, let me see. Gradual family of spectra. Yeah, family of spectra that satisfies Nyquist's first criteria is. We saw that, and we found out that what is the time domain function if at all I think r is 1. So this is called as a raised cosine characteristic, okay, or this is called as a raised cosine pulse. And then we were studying some of its properties. The best thing about it was that it decays rapidly 1 by dq. And why this rapid decay? This rapid decay allows us to have some sort of a leeway in our timing. Okay, जिस टाइम पे आप सैंपल कर रहे हैं, you can somewhat be relaxed. कि थोड़ा सा क्लॉक्स आगे पीछे हो गए तो ऐसा नहीं है कि सिग्निफिकेंट आया से नहीं जाए. सिंक के साथ ये समस्या है. सिंक के साथ क्या, अगर आपका टाइमिंग प्रॉपर नहीं है सैम्पलिंग का, if at all at the receiver you're not sampling the signal at proper instants or there is a gap in the two sample, तो ऐसा ही सिग्निफिकेंट हो जाए. ये I think हमने स्टडी किया. And this is very important. The last note which I have written, based on this note, let me write it down here. So the note towards the end of lecture 15 tells you that you need to take into account filters at transmitter, filters at receiver, and channel all together, and then apply Nyquist's criteria. Okay, so this is what is important. You will find that most of the development in hiking, that is textbook. So development in hiking, crouch, follow this approach from start. Follow this from start. Basically, they will start this section by this, but VP Lati first tells you the concept and then says this thing. Okay, so this is what is important to understand. Now let us start today's lecture. So today's lecture says, so we will start with example 7.1 from the Lati's textbook. Okay, this is important for us to study. We will basically see that this pulse shaping leads to what? So determine the pulse transmission rate in terms of the transmission bandwidth, okay, Bt, and the role of factor R. Now why it is said is कि अभी तक हमने क्या किया था, up to now we said that the bit rate of transmission is suppose R, bit rate was R, not rate of transmission, and if the bit rate was R, we were finding the transmission bandwidth. But the problem is now reverse. Given Bt, what best R can you support? That is the problem now. Okay, that is what this example tells you. Let me just write it more specifically what this means. Otherwise, once you will go back and read the notes, you can understand. So, given R, what is Bt? We studied. But so this is what is the premise of this example. So we have to assume a scheme using Nyquist's first criteria. Okay. So with this, we derive. I think you can just refer to the last lecture. We derive that B of T is equal to 1 plus R into RB by 2. RB is nothing but the bit rate. So I can remove B because sometimes I am using this B in the foot or sometimes not. So this is what. So this implies that if at all given Bt I need to find R, so R is equal to twice of Bt upon 1 plus. So this is important that ठीक है wireless engineers हैं आप अगर if suppose you are engineers who work in the domain of communications, so you will be generally given Bt, you will know Bt pre-hand because you will be told कि आपको स्पेक्ट्रम का ये हिस्सा दिया जाए, आपको बताया जाएगा कि ठीक है अगर आप even you are considering a 2-pair wire line, so our wire line has this much of attenuation for the frequency. It means frequency spectrum का जो data sheet है वो share कर दिया जाएगा. With that data sheet, you have to then determine your bit rate. Okay, so problem generally in the real world is you know Bt and you have to find R. But the study has been that given R, what is Bt? Okay, उसी से आपका ये आंसर ही आ गया. This is important. So let us write it down. So we know that the role of factor is always been 0 to 1. The pulse, I have not yet discussed very much about why R has to be 0 to 1. I am leaving it as a homework. Okay. Why? So this is a homework, and this can be asked in the exam. The last, you can say, the end some exam. That because this is very simple to determine. If still it is not clear, we can discuss later. Okay. So the pulse transmission rate varies from twice of Bt to Pt, okay, depending on the choice of R. This has to be clear. Depending on the choice of R. Quite obvious. A smaller R smaller r gives a higher sampling rate. Why? Because your R will increase. If bit rate increases, it means you are sampling at a higher rate. But PT decays. That is important. That is what we have seen. That will be a sync pulse, but PT decays slowly and makes the system sensitive to सैम्पलिंग एरर्स. ओके, इट मीन्स एट द रिसीवर पर अगर आपका क्लॉक जो सैम्पलिंग क्लॉक है वो गड़बड़ है, उसमें थोड़ा सा डिले है, तो वो इट लीड्स टू सीवियर ऐसे. फॉर द आरसी पल्स, दैट इज द रेस्ट कोसाइन पल्स, फॉर द आरसी पल्स R is equal to 1 and RB is equal to BT. It should be RY. Again writing P, it should not be, because this example started with R. And we achieve half the theoretical maximum rate. देखो कैसे हुआ. अगर आप सिंक पल्स यूज कर रहे थे, सपोज यू आर यूजिंग सिंक पल्स ड्राइंग करेक्टली. So if at all you were using the sync pulse, okay, so you were consuming a bandwidth of, let us say, this much. Now you have used the RC pulse. Suppose I am not drawing the RC pulse, suppose you are using RC pulse. So this leads to, let us say the spectrum is somewhat like this. That is, it consumes approximately R. So now, initially अगर आपको इतना बैंड, सपोज आपको 2 मेगाहर्ट्ज दिया जाता, so आप उसके अंदर अगर ये सिंक पल्स यूज करते तो आप R/21 मेगाहर्ट्ज का डेटा रेट सपोर्ट कर सकते थे. बट sorry, reverse of that. And if at all you are given this much, this should be R or R. And if you are given this much, so 2 मेगाहर्ट्ज ही गिवन है, तो 2 मेगाहर्ट्ज में आप आरसी पल्स ट्रांसफर नहीं कर पाएंगे, आपको मतलब रेट घटाना पड़ेगा. दिस यू नीड टू डिक्रीज so that you are fit into 2 megahertz. I think this should be clear, because जितना बैंड गिवन है 2 megahertz के अंदर, अगर आपको suppose 2 megahertz by 2 and 1 by 2 1 megahertz का रेट सपोर्ट करना है, तो you have to use a sync pulse. But with the RC pulse you have to decrease R, then only your RC pulse can fit in this 2 megahertz. Okay? This should be clear. That is what I wanted to say. Now let us shift to Nyquist's. So I just have to say a few things about the second criteria, okay, or method, second method or criteria, second and third, because I said that Nyquist proposed 3 criteria. Yeah, if at all you have any doubt or anything to say, you can just unmute and say, we can discuss. So some ISI, so this we are not going through, but this is important. Some ISI to be introduced in a controlled way, okay, in a controlled way. What it means is that first criteria completely avoids ISI. First criteria says that at the sampling times there should not be any contribution from other pulses, okay. But the second method says that let us accept some contribution from other pulses, and that contribution has to be in our control. कि कितना इंटरफेरेंस वो देंगी सैम्पलिंग टाइम पे, वो हम पहले से डिसाइड करके रखें. दैट इज प्रीटी मच मोर. तो इसमें आपका आ जाएगा 2 बाइनरी पल्स. The problem is I wanted to cover all these things, but I think we don't have time for this, because anyways we have to cover a lot of topics after this. So it depends. If at all this portion of 2 binary pulse is covered in section B, then I will come back into it, okay. I don't know whether it will be covered there or not, because still Professor Godgambar has not started Nyquist criteria there. So I'm just introducing it and leaving it. Maybe we can do it at a later stage if at all it is covered there in a controlled way, so that it can be cancelled, out at the receiver, okay. Basically, this will further ease up your process of generating the pulse. Okay, and the data can be recovered. The data can be recovered without error. Without error, if no noise is present. Because this is what is the second criteria is. Now let us go to the Nyquist third criteria, because Nyquist gave three criteria. Okay, Nyquist third method criteria, whatever you want. Okay, criterion slash method. Choose pulse. Choose pulse such that area within the desired symbol interval ts is 0. ts is not 0, but the area under adjacent symbol intervals is 0. Okay. Now the problem with the third criteria is such pulses have been found. Such pulses have been found but their performance in the presence of noise is inferior. So that's why this third criteria is not much under study. So this is what all I have to say about, you can say, Nyquist criterion, first, second, third criterion. This is a very, very important topic from the perspective of the general study of communication systems, or specifically digital communication system. Quite important from the perspective of interviews as well, for the perspective of research as well, because this tells you कि जो आप एडवांस रिसर्च करेंगे अगर इस एरिया में, तो उसमें जब इस तरीके के इश्यूज आएंगे, if such issues crop up that time, okay, then you know the answer, that how they are handled. Because mostly when you will be doing advanced research, all these things are not written in the research articles or in books there, because it assumes that you know this. So now you know this. So that is what the thing is. Now we will shift to another very important tool, that is the eye diagram. Okay. So we are done with the Nyquist criteria, and now we shift to the eye diagram. Now this is very important as well, because again the question that what is eye diagram? How will you study if the system is affected by ISI or not? So this eye diagram gives you an answer. So given the received waveform, the question is, how can you tell the signal suffers from ISI or suffered ISI? So that is the very, very important question. The receiver पे, suppose you have to design a receiver, or you have written 2-3 codes at the receiver. One code handles ISI, one code assumes that the ISI is not there, another code assumes that ISI is there but of a very limited value. So at the receiver, decide कि if at all I have a signal which I receive, and I need to process it. So which code segment I should put on it? Code segment means, suppose you have written the M file, or you write your code in C, or you write your code in Python, or whatever language in which the code is written. Suppose you need to debug that code to analyze the signal.
how will you determine that whether the signal which you are receiving is really ISI corrupted or not? ISI से corrupt हुआ है या नहीं? So this eye diagram gives you that answer. What it really does is, let me write it down. So this is the synchronized superposition. Synchronized superposition of all possible realizations of the signal of interest. You can say example is received signal, comma, receiver output. Viewed within a particular signaling interval. Now let us see what the meaning is. The concept is, suppose you have chosen this as your pulse. Now this pulse, let us say, consumes a time TB. Have I mentioned? No. Suppose this is the signaling interval. It means TB, you can say, or bit interval. You can say this is also about bit interval. Like right now, assume that we are having bits for transmission, okay, instead of symbols. So bit interval. So you multiply it with 1 and transmit. Then the next instant, you again take the same pulse. Suppose the bit is 0, so you multiply with 0 and transmit. Suppose then again you take a pulse, it is 1, then you transmit. Suppose then if you take a pulse and it is 1, you transmit. Okay. So this is a digital sequence 1010. You will add it all up. That is a formalized summation an p of t minus nt. Okay, that is the formula for generating the signal at the baseline. Suppose now what I do is that in an oscilloscope, if this is my oscilloscope's window, I set that this width corresponds to suppose t. Means मैं जो oscilloscope का horizontal sweep है, यानी जो horizontal you can say zero जो time axis है, उसको हम ऐसा कर देते हैं कि यहाँ पे 0 है और it takes a time t. And I superimpose all such pulses on each other. तो पहले जैसे 1 था तो मैंने उसको suppose ये बन के आया प्लस, फिर 0 के corresponding pulse आई तो उसके ऊपर I just superimposed. Then 1 के corresponding pulse I superimposed. So that is what I have done above. Synchronized means that TT length, मतलब आपने सिग्नल का TT स्निपेट उठाना है. आपने क्या किया, आपका सिग्नल इनकमिंग आ रहा है, आपने एक पहले टाइम 0 सेट किया, फिर 0 से T लेंथ का सिग्नल पिक किया, उसे प्लॉट किया, फिर नेक्स्ट T लेंथ का सिग्नल उठाया, उसे प्लॉट किया, फिर नेक्स्ट T लेंथ का सिग्नल उठाया और उसे प्लॉट किया ऑसिलोस्कोप के ऊपर. ये कैसे होता है, इसमें क्या होगा, आप हॉरिजॉन्टल स्वीप पे एक सॉ टूथ वेवफॉर्म लगा देंगे. हॉरिजॉन्टल स्वीप, देयर इज अ बटन और यू कैन सी देयर इज एन input on the oscilloscope. So on the horizontal sweep, apply I think that is a sawtooth waveform. I don't know. Apply a waveform. I've forgotten what the name is. I think it is sawtooth hai ya there is a standard rect waveform. I don't know. A waveform with on time, it means on time of t. एक टाइप का स्क्वायर पल्स मान लीजिए जिसमें ये इस तरीके से चल रहा है और मोस्ट प्रोबेबली दिस वुड बी टी एंड टी और दिस इज टी समवेयर. ओके, सो यू कैन जस्ट वेरीफाई, यू राइट इट डाउन, यू कैन वेरीफाई. सो दैट इज मतलब दिस इज व्हाट इज डन इन हार्डवेयर. हॉरिजॉन्टल स्वीप लगा देंगे तो उससे ये काम आपका हो जाएगा. बट राइट नाउ स्टडी के लिए हमारे लिए बहुत है कि हमें पता है कि एक के ऊपर एक हम पल्स सिस्टम लगा सकते हैं. दैट इज व्हाट सिंक्रोनाइज्ड सुपरपोजिशन ऑफ ऑल पॉसिबल रियलाइजेशंस ऑफ द सिग्नल ऑफ इंटरेस्ट. जैसे कि जो सिग्नल आपके पास आ रहा है, रिसीव सिग्नल हो या रिसीवर आउटपुट हो, रिव्यूड विद इन अ पर्टिकुलर सिग्नलिंग इंटरवल. तो सारे पॉसिबल रियलाइजेशंस को एक के ऊपर एक सुपर इंपोज कर दीजिए, सिंक्रोनाइज्ड सुपरपोजिशन. दैट इज व्हाट इज द आई डायग्राम. Now, how will this diagram tell you that if your received signal is suffering from ISI? That is what we will now see. Okay, so I have written in the notes. Let me write here. Okay. So on the vertical plate, why I am doing this or why I will be writing this is so that we at least somewhat know कि oscilloscope में कैसे होगा, जरूरी है जानना शुरू में, जबकि right now we are studying digital communication systems, not the concepts of CRO, but still we need to know somewhat. So on the vertical plates of an oscilloscope, we connect the receiver's response. We connect the receiver's response. We connect the receiver's response to a random pulse sequence. Okay. मीन्स सपोज जैसे ये 101010 आपने कोई रैंडम बिट सीक्वेंस जनरेट किया, उससे आप एक कॉरस्पॉन्डिंग पल्स जनरेट किया अपने ए ऑफ टी और उसको आपने वर्टिकल प्लेट पे अप्लाई कर दिया. मीन्स आप वर्टिकल पे आप उसकी वैल्यूज देखेंगे जैसे हमने प्लॉट किया. सिंपल. आई थिंक यू मस्ट बी नोइंग व्हाट डू वी डू इन ऑसिलोस्कोप, मस्ट हैव डन इन इलेक्ट्रिकल सर्किट्स, द बेसिक लैब. द यूज ऑफ ऑसिलोस्कोप यू मस्ट हैव डन. On the horizontal time base, yeah, it is a sawtooth waveform. So on the horizontal time base, we connect a sawtooth wave. We connect a sawtooth wave at the signaling frequency. Okay, that is important. That is horizontal time base of the oscilloscope. Horizontal time base of the oscilloscope is set equal to this symbol duration. We can say pulse duration. Now, step 1 and 2. So this is 1, this is 2. Step 1 and 2. Superimpose. So this will do this. Now, if you are an enthusiast who wants to know really that how the oscilloscope does this, based on these two things, you can just do a deeper study of the oscilloscope. Suppose once the campus starts offline, it means if you are on campus, then you can go to the lab and try doing this if this can. Okay. वैसे तो this is possible. Otherwise, ये study नहीं हो रही होती. But खुद करके देखना, if you want to do it yourself, then it's really fun. So you can do it. Step 1 and 2 superimposes the waveform. Superimposes the waveform in each signaling interval. Into a family of traces. In a single interval. Okay. In single interval 0 to t. So this is what happens. So let us see this. I think from one of our textbooks, I should say. Yeah, this is from Clark's book. But this is what is happening. This is the eye pattern generally. So आपने क्या किया कि 0 से लेके suppose this width is TB or T. So over T you are plotting the various snippets of, you can say, the incoming pulse. जो incoming sequence आ रहा है उसका आपने TT length का, you can say, वैल्यू लिया और उसको एक के ऊपर एक. तो आप देखेंगे कि शेप किस तरीके का है. This shape is that of a human eye. Okay, that's why the name is eye pattern. अब जब human eye बोली है या we have said that it is a human eye, then we have to see what is the width of this opening, what is the horizontal width of this clear signal which we get. Okay, what is the width, what is this, and what is this. So this basically diagram tells you the level of ISI in the received sequence. If this eye is quite wide open and this D of A is very small, it means its system has undergone very less ISI. Let me write it down for you. And one more thing you can see this, if we always see it from, you can say Latti's book, then, okay, I have not gone to the page yet. Let me just see it is on which page. Please, just hold on for 2 minutes. Let me check. We should see, then only we should proceed. 66. Around 87. Yeah, I did. So yeah, this is what is that. This is what I wanted to show it to you. So this BP Lathi, I think BP Lathi gives it in a very more clearer way as compared to Hicken also gives it, and Sklar also gives it. But all the three textbooks I found that they are quite well in presenting this eye diagram. But you need to go through all of them to have a sound understanding. So that is what I have done. I have taken my notes or my, you can say, content from each of the textbooks, and then I'm presenting it to you so that you have a fairer understanding of this concept of eye diagram. Okay. So this is the three possible eye diagrams. So first is that, let us say this is a 101, this is a random pulse, or you can say a random line code which is transmitted, and it is going through a band unlimited channel. Theoretically assume your channel is band unlimited. It is not having any sort of clipping in the frequency domain. Then whatever you transmit, you will receive as it is. And the eye diagram, suppose TB length की मैं snippets लूँ और plot करूँ एक के ऊपर ही, तो block box बन के आएगा. क्यों? Because थोड़ी देर के लिए कहीं मतलब for some time the waveform is 0, for some time the waveform is 1, so it will have both the levels. And if I plot it over a width of 2 dB, then again it is a box. But now assume that this is the waveform which is going, okay? Which is exactly not the square waveform, which it won't be in most of the cases, because you do not have band unlimited channel, you have band limited channel. So you have designed or you have smoothened out the pulse. So let us say the pulse is of this form. And what you are using is, you are using a binary PAM type of a system, or you are using the first unipolar, no, actually bipolar, that for 1 you have a plus, for 0 you have a minus. So you will have the eye diagram as exactly a eye. Okay. But now assume the same pulse going through a band limited channel. Right now the wave is band unlimited, so that's why it's a perfect eye. But now if at all this goes through a band limited channel, so you will observe that the waveform is now this. ऐसी हो जाएगी waveform. See, that is what is now really shocking, that you have transmitted this, and once it is going through the channel at the receiver, the waveform is like this. For this waveform, if you try to plot the eye, so see, this is what happens after passing through the band limited channel. So this eye, which was clearly open, is now somewhat getting closed, because this line shows that now the eye is not very wide open. And for over the 2B interval, see, this is what is happening. So this shows that the system underwent ISI, okay, or extent of ISI will also get to. So this is what I wanted to tell you. Let us now go back to our notes and write. So one important thing, note that why do we get the eye diagram like that is, in each pattern, because the symbols in each pattern you see, this because the symbols stem from a random source, They are sometimes positive. They are sometimes positive and sometimes negative. It means because random source है तो कई सारी possible values हो सकती हैं, इसलिए आपको box दिखेगा या एक आई पैटर्न दिखेगा. Sometimes negative. And the persistence that is important, and the persistence of the cathode ray tube display, cathode ray tube display allows us to see the resulting pattern shaped as an eye. The resulting pattern shaped as an eye. Yes. So this is what we wanted. This is the explanation for these things like this. Okay, कि आई कैसे बन गया, मतलब इतनी सारी हमें लाइनें क्यों दिख रही हैं या नीचे भी हमें क्यों दिख रहा है, क्यों? क्योंकि our the bit sequence which we are considering, or generally it would be random. It will have some transitions for 1, some transitions for 0. It means 1 0 1 0. As said, it might be there that you have a big stream of ones, but generally this is avoided by channel coding or some sort of a coding where you do avoid long streams of 1 or long streams of 0. Okay, so you can assume that there is a healthy distribution of ones and zeros in the bit sequence or the pulse which you are getting or the line code which you are receiving, and hence because of this you will have both the shapes. Persistence of CRT means that the time in which it changes the display. So that is somewhat not very, you can say, exact or very good for our pulse sequence. So you will see that both the diagrams. Okay, मतलब इसको, this is the beauty to visualize it on hardware basically. अगर आपके पास, if you have let us say you are in on campus in the lab, and then you can visualize it, this you can visualize it how this happens. But this is really, this is used in industry as well. Okay. Now let us see some of the parameters of it. So width of the opening. Yes, someone is unmuted. You want to say something? Yes, I think, okay. So you have muted yourself back. Okay. So width. See, these topics are important, I would say. ऐसा नहीं है कि ये just we are doing it for the purpose of making the course, you can say, tougher or something. No, this is important. This is easy to understand once you go through it. And being BTech in ICT, you have this information and communication technology as your specialization of BTech. So you must, I feel that you must understand the subjects dealing with communications as well as those for dealing with information. Okay, information and communication technology. अब information की सिर्फ coding पे ध्यान देंगे तो कैसे काम चलेगा? थोड़ा सा उसका transmission पे और उसकी study पे भी ध्यान देंगे. That is what I would suggest. So width of the opening. Indicates the time over which sampling for detection might be performed. Okay, this is important. We will see it through the figure. Might be performed. Okay. Then the optimum sampling time. Sampling time is equal to the point at which eye opens the most. Max eye opening. जहाँ पे सबसे ज़्यादा आई खुले हैं वहीं पे आप सैंपल करें सिग्नल को तो it will have least access. Let us say you can see that the eye is mostly open in between here. or you can say at this point this is the point where the I is maximum. So this is the sampling instance. So this I diagram tells you at what point you can sample the signal which will lead to the least possible ISI. Okay. So max I opening, this is equal to greatest protection sorry yes this is what I have said is not exactly right. Why this tells you the exact point of sampling is that if at all you have additive noise in the system, if right now we have not considered additive noise, we have said that the channel, that the signal is going through a band limited channel, but we have not yet assumed that something adds to it. Now suppose some random noise adds to it. So the margin for, let us say यहाँ पे है अगर, चलो मैं लिख लूँ, let me just write it down. The greatest protection against noise. Protection against noise. Okay. So what we are saying is that suppose if this is your what you are transmitting. Okay. Now if something adds to it, some noise adds to it. Up noise, and you are using some sort of a bipolar or unipolar scheme, or you can say that you have two levels, and another level is this. And the receiver determines that if at all suppose this is 0, if your received value, the sampled value is greater than 0, then I will consider it to be +1 or 1, and if at all it is below 0, I will consider it to be 0. Suppose you encode 1 with a positive pulse and you encode 0 with a negative pulse. Okay. Suppose this is what you do. And 0 with a negative pulse. So receiver अब इस bit interval में suppose TB में you sample this up, and once you sample you collect one sample. Okay, collect one sample. Suppose collect one sample in T. Okay, एक sample collect कीजिए. Suppose you collected this, and once you collect this sample, it will check if it is greater than 0, then 1. It will say that 1 was transmitted. If it is less than 0, then 0 was transmitted. Up suppose noise adds into the system. Now this noise will change this level. So the margin which the noise has to create an error is this much. If at all my noise value is suppose this length and in the negative, so it will take my signal to the down level. So if it takes in the down level, then I transmitted 1, but I will decode 0. So this says कि जहाँ पे I सबसे ज़्यादा open है, suppose if this is the place where I is maximum open, you sample at this, because this makes the signal immune to edit, or the effect of additive noise will be least on these points. Okay, this is what this is. Okay. Now I think one more fact which I need to write is that if channel bandwidth or transmission bandwidth is infinite, is infinite, system response would yield rectangular pulse shapes. Okay, I think this we have already seen. Pulse shapes looks like box. Okay, so that we have already seen. So this is pretty much what I wanted to say. Let us first discuss what these terms are. So this is M of N. Suppose this is S of T. This is D of A and J of T. So let me write down what these terms mean. Okay. So Mn is noise margin. Okay. St is sensitivity to timing error. Jt is timing jitter. And Da is measure of distortion caused by ISI. So let us see what is the corresponding terms. So M of n, we said that it is a noise margin. It has to be, because this is what, if at all noise is greater than this noise margin in the opposite sign, then it will definitely lead to errors. Only this much margin we have with regard to the noise it will add to the system. Okay? इससे ज़्यादा अगर रिवर्स में नॉइज ऐड करेगी तो डिटेक्शन एरर पॉसिबल है और होगी ही होगी. बेसिकली इट विल लीड टू एरर. Then S of t, this S of t is the sensitivity to timing errors. Now why? Because this says that I can sample my signal. It's not necessary I sample in between. I can sample anywhere in ST. Okay. If I sample anywhere in ST, I will need to, you can say my result would be somewhat right. Only this much timing error I can afford. But because if I exceed S of t, then either the signal value I will get is 0, okay, or I will be sampling another pulse. Okay, मतलब next जो आपने transmit किया वो आप assume कर लेंगे पहले. So this tells you that this is your sensitivity to timing error. Then J of t is timing jitter. Okay, now these are two separate terms. One is S of t and one is J of t. I will go back to the notes and explain it to you in some more detail. First, let us see what is D of A. So D of A is measure of distortion caused by ISI. Okay, it means कि जितना नहीं तो देखिए अगर आपने आइडियल पल्स होता है जो हमने यहाँ ड्रॉ किया है तो यहाँ पे सभी पल्स का लेवल सेम होना चाहिए. बट अगर जिन जिन पल्स का लेवल सेम नहीं है, अगर आपने ऑब्जर्व किया, यू ऑब्जर्व दैट नाउ दिस इज समवट लाइक दिस, सो जो सैम्पलिंग पॉइंट्स थे, जो वो पॉइंट्स थे जिसमें हमने कहा था कि इट शुड नॉट इंटरफेयर विद अदर पल्सेस हैव नाउ बीन डिस्टर्ब्ड. सो दिस इज डी ऑफ ए, टेल्स यू द मेजर ऑफ डिस्टॉर्शन कॉज्ड बाय आईएसआई. Now first see what is timing jitter and sensitivity to timing sampling. Okay, it's timing jitter. So since timing jitter is, let me write it down. What is timing jitter? This we should know. This is a deviation from I think somebody is unmuted. Okay, Paras. So do you want to say something? So he is not there. So deviation from presumed periodicity. Deviation from presumed periodicity. Now what is the meaning of it? Now let us see. If suppose you assume that my signal should be periodic. So if at all, at this point, it should have a zero transition for all possible waveforms, which it is not. Okay, it means that the system की जो periodicity है वो थोड़ी सी receiver पे गड़बड़ा रही है. Simple ये meaning है कि जो jitter है means अगर आप suppose, let me tell you one thing, that if suppose this is your sine, this is what I am transmitting. So I assume that signal being periodic, this should have a zero value at this point. And it should have this one value at this, then again 0 at this. Suppose you will have -1 at this and then 0 at this. Suppose this is the periodicity, presumed periodicity of sine wave. But now suppose I receive a sine wave like this. This though I have perfectly drawn with the perfect delay. You can say that I can correct it out of the delay, but this is just for the purpose of giving an example that instead of this point, the function is having a 0 at this point. Then here I assume the function should be 0, but it has a different value at this point. So this is a deviation at the receiver. The signal has deviated from its assumed periodicity. जब हमने कहा कि अगर t equal to 0 पे 0 होना चाहिए तो 0 नहीं. t equal to suppose pi by 2 पे अगर this should be 1, but it is not 1 at pi by 2. It is somewhat a different value. So this is timing jitter. So this it tells you that कि जितना या 0, देखिए जितने width में सब zeros आ रहे हैं बाकी pulses के. So this is timing jitter. इतना हमारे लिए right now समझना, I think I would say that is fine, but we are not doing deeper into the study of eye patterns, जो कि जाना चाहिए, but as you know that always we are restricted in time because the topics we need to cover in some course. Okay, So you cannot do much. So let me write one more important comment with regard to the eye diagrams which we have studied. So in the case of M airy, you can say M airy systems. We have up to now we have studied binary. Okay, let me write it down that up to now we have studied binary. Up to now we studied binary. The eye pattern contains. This is important to understand. The eye pattern. What will be the eye pattern in the case of M area? M area means, I think in our course up to now we have not done M area. We will do it subsequently when we will study MQM and all these modulation schemes. First of all, we are building base for that study. Okay, so the eye pattern contains M minus one eye openings. Okay, M minus one eye openings stacked up vertically. Stacked up vertically. One on the other. Okay, one on the other. Where M is the number of discrete amplitude levels used to construct the transmitters. Okay. For this, let us see the figure that how really this is. So this Haken has showed. Let us see. So this is what is the eye diagram for an M-airy system. So that is what we have written. That in the case of M-airy systems, the eye pattern contains M minus one eye openings. So let us say 1, 2, 3. 3 eye openings are there, stacked up vertically one on the other, where M is the number of discrete amplitude levels used to construct a transmitter. So why I wanted to show it to you is that sometimes the question is that basically you know कि binary system का eye diagram कैसा होगा, but the question is that most of digital communication systems are M-airy. So what will be the eye diagram of that? And there we falter. We don't know that. So it should not be after doing this course. So that's why I just shown it to you that this is the eye diagram for an M-airy system. Okay. So then I think we are done with the concept of eye diagrams. I would insist that you go back and study it, and if at all you have doubts, we can have a separate session to discuss. But if the doubts are in general, it means a lot of people have it. We can discuss it in the class next lecture. Okay. Now we start with the concept of signal space. Okay. So the third concept for today is signal space. So ISI, Nyquist ISI criteria and way to visualize ISI we are done now. So we are now going to study signal space, where we will be studying the Gram-Schmidt orthonormalization process or orthogonalization process. And with this as the background, then we will go to random process. Okay, we will study some random processes, where the most important random process for the course of digital communication is additive white Gaussian noise random process. Once we do that, once we are done with the random process, then our study for modulation schemes will start, because at that point we are well prepared to now simply deep dive into the modulation schemes and their detection. Okay. So signal space is very easy to study right now, because you already undergo a course on groups and linear algebra, and you know that there is a space, there is a vector space, basis functions, projections, and all these things are covered there. So the load to teach those concepts is now reduced for the post digital communication. We will simply now study what we need. Okay, assuming that we have a background in these things. So first of all, a definition. So what we'll be using? So let ST be a full duration. Full duration means T seconds. T seconds. real valued energy signal. Real valued energy signal. Now, what do you mean by that? That is 0 to t. So right now we are assuming that s of t is, we are studying s of t in 0 to t. It has only a duration of t seconds. Now why? First of all, the question is why are we going to study only signals which are limited to t seconds? Because generally हमारी pulses होंगी या जितना भी हमारा ट्रांसमिशन है वो हम स्टडी कर रहे हैं एक बिट इंटरवल में. सो इसीलिए हम लोग सिग्नल स्पेस की भी जो स्टडी कर रहे हैं राइट नाउ फॉर डिजिटल कम्युनिकेशन इज फॉर ऑल दो सिग्नल्स हु आर समवट टाइम 0 से t के बीच. क्योंकि हम इवन अप टू नाउ व्हाट यू सी इज दैट हम बिट इंटरवल के रिस्पेक्ट में ही सब कुछ स्टडी कर रहे हैं, ये सिंबल इंटरवल के रिस्पेक्ट. ओके, सो रियल बोले हैं मतलब इफ यू हैव said that s of t is real, so in order to calculate the energy you simply take a square dt, okay, and that is less than infinity. It means a finite energy signal. अगर ये complex होता तो इसका आप absolute value लेते. Okay, I think this you are quite well taught in signals and systems. If complex होता तो आप ऐसे करते हैं. Absolute value को square for complex. So now we will go to geometric representation of signals. First of all, we will study geometric representation of signals. So our purpose of doing this geometric representation, now ये बड़ा एक you can say an intriguing concept. हमने अब तक पता था कि signals जो हैं they are functions of time. Okay? Functions of time. But now we are talking of geometry. It means signals we can study as we study things in geometry. So this is what is the premise of what we will be doing. And this really opens up a lot of things. Why? Because geometry is quite well developed. And if at all we can represent signals as elements in geometry, then we save ourselves from time basically. Otherwise, if I talk of s of t as a signal, even in, you can say s of t in t belonging to, you can say 0 to t has infinite values. Okay, तो t आप बदलते जाएंगे 0 से t के बीच में, तो it has infinite values. So for studying it, you need to carry those infinite values together. But for, if at all, you can have a geometric representation, or if I can associate a finite length, if I can associate a finite length and think to it, the study becomes easier. Okay, study can become easier and we can do a lot more things. That is what is the concept behind having a geometric representation of signals. Okay. So the purpose is that, let us say you have set of m energy signals. Energy signals I have already told you. Right now we are in the real space. Okay, it means all the signals are real. Generally real world में real signals ही होंगे, but because complex quantities help us model several things, we study the complex space as well. But right now at the undergraduate level, or for the purpose of our digital communication study at the basement, this suffices that we can consider the signals to be real. Okay, so set of m energy signals. The purpose is as linear combinations of m orthonormal basis functions. Orthonormal basis functions, where n is less than 1. Okay. That is, what do we want to do is SIT is equal to summation j is equal to 1 to capital N Sij phi j. T I is equal to 1 to so this is what is our purpose. Yes. Where let me just complete this before we close for today. So where Sij is equal to integral 0 to t SIT pi j t dt for and I is equal to 1, 2, 3. Okay, and what are phi jt's? Phi jt's are orthonormal. Phi jt's, the set are orthonormal. That is 0 to t phi I t phi j t dt is equal to delta ij, which is equal to 1 and 0 if I is equal to z, if I is equal to j, and if I is not. So pretty much this is what we want to do at the moment. So I think we can continue ahead in our next lecture, in our next class, and we will discuss the signal space somewhat in a more involved manner before starting to do something new. So I think we're done for today. Those who want to stay to discuss something, they can, others can leave.